Thank you for coming, and thank you to the organizers for giving me a chance to speak about this topic, which I feel very passionate about. Yeah, let's get going. Title is Scaling Up in Scope, How to Use CI/CD and Unit Testing to Ensure Quality and Correctness as your Databricks data platform grows in size and scope. And I chose specifically in scope because you always hear about scaling your computing power and making your tables bigger and making your clusters bigger. But how do you manage the complexity when you go from maybe like 5 tables to 500 tables? Because it's just going to be a much more complicated product to manage. So in one slide, what I'm going to talk about, I'll first introduce the problem that I'm trying to solve. Talk a bit about literature and what we can learn from other subjects other than the data people. And then I'll really get into how I do testing. And specifically, I have examples about how to do testable code. Because that's kind of where we're getting deepest into the details. And then I'll just wrap up and talk a bit more about the bigger picture of how this fits into this. A little bit about me. I am educated as a particle physicist. I've worked at CERN on like really big data, where we have data sets that are like tens of petabytes, which are millions of terabytes. And since then, I've worked in defense and energy companies, where I've learned to build very reliable systems at big scale. And then the past 4 years, I've been working on a Databricks data platform for a company in Denmark. And I will mention them a bit more. And for your information, since January, I'm a freelancer. Let's start at the beginning. I'm starting at the point where the usual tutorials finish. So you've got your you started using Azure Databricks. I only use Azure, but I'm sure it works in other clouds as well. You've got your machine running. You've got something that ingests some raw data. There's a guy who's controlling some master data. Someone is in charge of operations, and then someone is like taking out the graphs and checking, making business value out of this data platform. And so let's assume you've already sold that to your business people. They see, oh yeah, this makes total sense for our business to have, and it's in production, and you've got it running. So what's the next thing that happens? Next thing that happens, hopefully, is that they say, this is so great, we want more of this. We want you to add another functionality. We want you to add another set of tables. We want you to add a second source of data to ingest. And of course, you don't start over from scratch. You don't build a new data platform for that. You're going to build on what you have, extend your existing deployment, and add another 3 notebooks or something. What happens next is they ask you to do more of that. Then you've got 10 notebooks. Then you think, okay, we need to, use some shared code here. We need to reuse notebooks. We want to, make this more efficient, more professional code. And then as you grow and grow, it gets really hard to keep an overview of what you have, to keep how do you still maintain, even though you added new functionality, how do you maintain the quality of what you've already got, the stuff that your business users are already depending on? How do you ensure that every time you add new stuff, everything else keeps working? Now, before I actually tell you how I do it, I'm just going to tell you that this is a problem in software in general, which has a lot of literature behind it. I've worked in a field called systems engineering, which is the science for how to do, or the engineering study for how to do really big systems, like go ahead and build the space shuttle. What do you need? That sounds like a completely unsurmountable problem, or like build the bridge that connects Denmark to Sweden. It's a huge project, which affects a lot of people and touches on a lot of technologies. But there are ways to break that down. And of course, to break that down, you want to gather your requirements. What do I need to solve? Talk to all your stakeholders, and immediately start thinking about how are we going to end up checking that we actually fulfill those requirements, because it's no use gathering requirements which are untestable or uncheckable. And then you start by breaking your system, your top-level system, down into components, your modules, and they have interfaces. And then each of those, they will have functions assigned to them and requirements. And then on the next level down, you do the same thing. You check how am I going to check those requirements, and then how do I break it down until you reach something which is a unit which is simple enough that you can just build it or program it or buy it. And then you start integrating from that. Well, do those pieces fit together? Are the interfaces, do they work, and so on? And you test all the way up until you get to a finished product. That's called systems engineering. You can take whole university courses on this. So one slide probably doesn't do it justice. In practice, of course, you're going to iterate this. But testing is a core part of any big project. In software development in general, these days, you have a standard practice which is called the pull request flow, or continuous integration and continuous deployment. And the line at the top represents like the project in general, which is just keeping on its own life. It may have other changes coming from other directions. But what you do at the beginning is you branch out, you make your own little copy of it, and then you start developing and applying changes to that to add the functionality that you want to add. Once you're somewhat happy, you open what's called a pull request. And a pull request means that it's like a discussion page, and usually it also activates an automated system that starts executing all your tests against this version, this alternative version of your project. And those automated tests, they of course have to be written and maintained, and that's what I'm going to talk more about later. And this part is called continuous integration, where you regularly test everything. And you test all your integration tests. Then in practice, you will have to go back and do some more, but then eventually your superior or your colleagues are going to approve your changes and say, we agree, all the tests have run successfully, it looks like you've added new tests for your changes, we can merge that. The merging is usually automatic, and then comes the deployment part, and that's the continuous deployment. Continuous also means, again, you do it regularly. You don't just wait for maybe develop for 6 weeks and then you have a freeze period where you deploy the new system. Continuous means you do this regularly, and I do it at my job. I do it several times a week, sometimes several times a day. We deploy to production directly where it meets the customers. And by doing this regularly, you know that you always got the latest system, you've always got the latest features in production. And all your deployment mechanisms work. In case something breaks, you can always deploy again. You don't have to, stop the world and deploy for a week or something. So that was just a bit of theory, a bit about how other people do it. But we're building a data platform. We're not just developing code, and we're not building a bridge. We have concrete questions we have ETL code, which does all the transformations, and we have tables which are in production. And all of that needs to be working together now and in the future with the changes. So you can ask questions like, does the code run against the tables that I expect to have? I call them described. I'll tell you what I mean by that in a minute. Will the code run in the way I deploy it? So does it have all the dependencies, the libraries installed? Is it correctly using does it use the features of the runtime version that you actually want to use in production? And then how do you actually evolve your tables from whatever way they look today to how you want them to look? So here my guy, he's looking at this machine and he wants to change it to a different wheel. It just doesn't yet fit, but he has just to make it fit. Isn't ChatGPT great for making pictures like this? So you have a choice to make for how to test this. You can test manually. And manually testing is something that just looks very appealing on the surface because it has a low cost of entry, because you've built the machine to do a thing. You just make it do the thing and check if it does the thing. And so it's easy to get going, but it takes a long time because the thing you want it to do usually takes some time. Then you have to make it, you have to set it up manually, you have to check that it does it manually. And so as you grow and scale, that's going to scale really badly. Automated testing has a much larger setup. And here he's like built a machine around the machine, and he's put a lot of wires into it, because you have to make your machine testable in order to test it in an automatic way. And this machine that tests the machine is also something that needs to be built, it needs to be maintained. And so it has a maintenance cost, and it has a larger entry cost. Problem is that, the thing is, automated tests, they will find your problems much earlier and much sooner. And automated tests have a lot of value. And that's basically the main takeaway of my presentation is automating your test is really, really valuable, and it really helps you to scale. By automating too late, you actually often times, and you start up, I've heard this so many times, we don't need to do test automation, we don't need to do configuration as code, we do just a simple thing. And then you've built the simple thing, and it works in production, and then someone says, okay, change it, add more, do more. And then you get exactly what I said in the beginning, that just eventually you'll run into this point where you said, okay, we didn't automate our tests, we didn't automate our deployments, and now it's too expensive, or we don't have the budget. But if you start this from the beginning, if you think this as part of your process always, whenever you start something, automate your tests, automate your deployments, it really pays off. So scalability, and that's like kind of the thing that relates to the title in my presentation here. So say you're going with the manual testing route, and you have the first feature, and there's some amount of effort to make the code and to deploy it. Then you also have to test that. And that's also some amount of effort, whatever how much that is. Then someone asks you to do the second thing. And it's, again, some amount of effort, and then something to test. But then you have to retest everything that you did the first time around. And that's going to come on top. And that already makes your second feature more expensive than your first one. And then, of course, you go and add more code. And again, just whatever unit that is doesn't matter, but there's some work to add something, and then the work to retest everything grows and grows and grows. And so your kind of velocity and your efficiency of extending your data platform, scaling your data platform, is going to be going down. Whereas with an automated testing effort, you have some amount of effort to add the thing, and then in the beginning it's going to be quite a setup to get going, or you can use my template, which is a little easier to get going, which is open source. I'm going to get back to that. And that's good. Initially, this is going to be more effort than a manual test, definitely. But when you get to the second feature and the third feature, the effort does not increase. You don't have to add more and more and more retesting, because every test is automated. And so adding another feature, you can automatically be sure that the first feature will stay good. And if you break it, you can notice and you can fix it. Of course, you get better at coding, and you get better at building the tests also. You can have fragile tests which, only work, I don't know, maybe you assume that all data older than 90 days is garbage, and you throw it away, and you make a test which just says, this is my test data and it should go through. And then at some point, this test data has timestamps which are older than 90 days, and then 90 days later, suddenly your automated tests start failing. And you're like, you have to think about it, oh, what did I do? Oh yeah, there was this 90-day check. And then you have to make a test which is either dynamic, or you kind of manually fix the timestamp of your filter. There are challenges, no doubt about that. But this really will scale. And I'll tell you my experience with this in a bit. So how do you go about automating your tests? Well, you have to select where your tests will run. You could use a local Spark session for Databricks. You could use Databricks Connect to test from a test running machine and connect to a Databricks cluster. or you can package all your tests and your business code and ship it up to run on a job in Databricks. I use all of those. The bottom one I like most, but it's also the slowest. You can also think about, well, what kind of framework, testing framework do you want to use? And now I use PyTest and unit test, which are testing frameworks in the Python environment. But that also means that all your code should be written in Python, or at least be somehow callable from Python. Now, Python is a general purpose language, so it's able to, even if you have large parts of SQL script, you can still, in Python, call them in and ask Spark to execute them. But mainly the main structure of your code is going to have to be Python. Or probably Scala can do the similar thing, but this is what I use. Now, also you have to think about how you modularize your stuff, because if you want to make it testable, you have to be able to refer to bits of your code. And referring to bits of your code is something which is, there's a standard process in programming called object-oriented programming, where you build classes and then you can instantiate those classes and call the methods on them. You can use notebook reuse, but again, it's going to make it more difficult to argue in your test description of what do you call and how do you configure it before running it and so on. Programming in actual Python classes is a more professional way of doing it, I would say. You have to think about how you instrument your code, because you cannot just take your production notebook, which maybe looks like this, and just say, okay, now I just want to run it as a test. You could do that, but you'd have to be on a different workspace and have, like, maybe now you have different schemas or something. That's one way of isolating your tests. I'll show you how I isolate my tests, because I have literally like 50 databases, and I have like 30 catalogs, and I have 500 tables, and so I don't use any of those levels to separate them. I will talk about how I do this. You can do something in Python called mocking, where you actually kind of modify what a Python call does. So you can say if you call spark.table, don't actually go to Spark, you go to my mock object, and then when you call this, it will actually, that's one way of doing it. So you can instrument code which is not written to be instrumented. But I find a much clearer way of instrumenting stuff for testing is to do dependency injection, where you explicitly say somewhere in a parameter, now you're running on a production system, now you're running on a test system. And so this code, you're going to have a hard time automating that for testability. But so let's get into how I instrument my tables for testability. So conceptually, every table exists in two places. It exists as the data on disk, and that's what I use this symbol for, and it exists as a description, hopefully, somewhere in your code. Somewhere you said, deploy this table. Of course, everything should be in code, not just your infrastructure, but also your tables, because having it in code allows you to test stuff. So you could also call this the desired versus the actual state. Now, when you have a table which exists in some version 1, and then you're making your pull request, which I've already mentioned, and you say, now I want to change that to version 2, and then I have some transformer code which also needs the table to be in that version 2, because, I don't know, your fields are changed or whatever. You don't want to change the production table until you've verified that the transformer works with that table schema. But the transformer, because it's Spark ETL code, it needs some table to run against. But you don't want it to be that table, because so you've got a chicken and an egg problem. Also, if your transformer code includes code like that, that's just not going to work. So here's what I do. I take a table statement like this, and I add this curly bracket. There's something here called ID. And that means that I template this entire SQL statement, and in a production situation, I will put an empty string here, so that my table actually is called raw data and nothing more. But in a test situation, I template this and I add a unique identifier. And it's different for every test run so that I can run multiple tests in parallel and they will not interfere. Now, if the table changes name, you need something which doesn't change to be able to refer to it. And so I have added some code which puts, this is just a key which identifies, there's a comment here in the SQL code and a key called my data table. And that thing doesn't change. And that gives, so that what that means is that I've introduced a new layer of abstraction on top of actually reading and writing tables. I don't read and write tables by their name, I read it by this handle. And for that, you need some tooling support. Now, my tool library is called Spettler. It doesn't mean much, it's just 6 letters that were free. And it's totally open source, you can find it on GitHub. So the most important class probably is this thing called the configurator. And the configurator here, if they assume this is a file and it's in this folder called SQL and in a package called demo. And the configurator, you can tell it where your SQL code is, and it will actually read the whole thing. It will read the SQL. So I've had to write a SQL parser. And this SQL parser, it will find out that here's a key, and it's next to this table statement. So this key will refer to that table. And I'm able to argue about the table in code without ever having deployed it. So I can tell you that it's there, and I can tell you what its schema is. I can tell you its properties, and if it has an external location, stuff like that. Now, in a production situation, I have what's called a delta table handle, and it uses the table configurator key from my data table. And if I do .read on that, I will get the production table, which doesn't have the extension. But I can go to my, now these silly controls down there didn't test it properly. They're gone. So in a test situation, I would again set up the configurator, and then I choose to set debug. And then when that is set to debug, it's like a global configuration object, then the exact same call will not read the table without the extension. It will read the table with some unique identifier here. And then, of course, this is just one piece of the puzzle. You also need to deploy these test tables in order to be able to run against them in a test situation. But so my transformation code, it's all using this delta handle. It's a class which can be instantiated based on this thing, and you can argue about the schema. You can read it. You can write it, and that allows me to run code like this in my production. This is how my production runs. And the tests are running extremely similarly, except there's a call like this beforehand. And that's how I'm able to test multiple parallel runs of the code before deploying it to production. So basically, the description of the table goes to version 2. I deploy a debug version, and then I run with the transformation of version 2. And if that's all good, then I merge my pull request. And deploy to production. What happens in the deployment? That's another piece of the puzzle. My deployment script, again, will use this configurator to take the schema that's in the SQL file, and it will compare that to the table that's already on disk. And if that's a match, there's nothing to do. If there's no match, you would have to make a decision. How do you then apply those changes? Now, in some cases, you want to just drop the table and recreate it because it's actually not a valuable piece of data. It's actually just a data product that's based on more fundamental sources. And this is what I do most of the time. In some cases, if it's just a column that's been added, you can just add the column and evolve the schema in order to, again, make the data table match your description. In other cases, you would actually want to throw an error because this is a table which should not be automatically evolved. And ideally, that error should be raised at the pull request stage and not, you shouldn't be running into that error by the time you deploy because then your deployment's broken. But But all of that is, of course, there's more code of this and more tooling. Again, some of the tooling is in my open source library. And then once you've deployed, then you've got your version 2 running, version 2 of your transformation code running against the version 2 of your table, which now matches the version 2 of your description in the code. So this is how I, when I make a change, I do a pull request, and my pull request tests every transformation of every piece of ETL code I have against every table that's in my data platform, and it checks that everything still works, even if I have some master data tables which has been cleaned and enriched, and then it's joined into 5 different places, and then you have to change the master data table. Does it still work with every other join that's going to be that it will be part of? And so this test is not just done for one piece of ETL code. It's done for everything in my data platform. And that's how I know when I make a change, it will work in production. And I would say 90% of the time, I catch all my errors in the pull request stage, and it happens rarely that something completely breaks when it hits production. Especially what this, of course, I'm not here going much into what's the difference between an integration test and a unit test. A unit test usually would be to say, well, in this piece of ETL code, I expect to be able to, I don't know, explode, filter, merge these fields, and I expect to get these data rows out. So you give it some key pieces of input, and you say this is how it should work. An integration test is when you actually put that into the context of the entire data platform. Does it still work? Will it break my flow? Because that's oftentimes even worse than producing wrong data, is to produce no data at all. And those integrations I can usually catch. So what's that look like in the real world? My experience with this approach, I use this extensively and have used it for 4 years. We've open sourced our tooling as much as we could. It's on GitHub. You can get it if you want. There are about 12,000 lines of code, and those 12,000 lines of code are extremely well tested. There are 15,000 lines of test code. So in this open source library, every time we make any change, because it's our fundamental stuff that really has to work correctly. So before we accept any changes, we run this pipeline which sets up a complete Azure data platform with Databricks workspace, with a SQL server, with the storage account, with Key Vault, with event hubs, and all of that is deployed. Then we run a complete set of transformations against a set of test tables, and only when everything is okay, then we just flush away the entire Azure infrastructure again and say now we can call that a good set of changes. So this is how we run. It's actually surprisingly cheap to spin up everything, and because it only lives for half an hour whenever we make changes. This is the company I work for in Denmark, and there I checked yesterday. We had 74,000 lines of ETL code and table descriptions. We've been doing this for more than 4 years. And for that, we have about 30,000 lines of tests. So this is a fairly sizable piece of software. The tests are currently running in parallel in like 7 or 8 job clusters, and they are running. All the tests are taking an hour to run. But in that hour, we test absolutely everything. And so when we everything is locked down. So the version of our Python dependencies and everything is locked down. And before we update anything, we run all of our tests. And when they're good, and we can deploy to production. And deploying to production, like I said, is an automatic thing which takes about 30 minutes. And we are running again. Using this approach, fully automated testing on absolutely everything, configuration as code on everything from infrastructure to table schemas. When I joined 4 years ago, we had 43 tables in our data platform. And those 43 tables, we had a team of about 5 to keep adding features. Today, we have 428, so that's a 10 times growth, 428 tables. and this many lines of ETL code. And for those 430 tables about, we have the same 5 people. Not the same people, but the same size of team to manage this data platform. Because we keep adding functionality, and we keep adding new data sources and new use cases, but we actually kept the same team size over a 10x growth. That was just in the number of tables. The number of users and the amount of data that's going through has also grown through more than a factor of 10. But usually data content growth doesn't cause you more work, not that much. But having many more business functions in our data platform, that has been possible by automating everything we do. I want to just add one piece of insight, which I feel is my personal thing. It's a psychological aspect. Engineers like building stuff. I like to build stuff. Engineers don't like sitting down to have to run through a manual test procedure. And if you ask your engineers to build an automated test system, they will be happy. And they will do good work because you're drawing on their core strengths. And so actually being allowed to automate everything, it's an investment, but it's also something which keeps your team happy. My opinion. So a little bit of a summary. There are a lot of pieces that have to be in place before you have a fully automated test system. You have to have infrastructure as code for everything. I recommend Terraform. Databricks has a great Terraform provider. You should probably have non-production environments. So the entire data platform that I've described, I have it in 3 copies. I have a development copy, which I can freely change it. Then I have a staging copy, which is fairly stable, and we test all of our deployments on the staging environment before we go to production, which is the one that's actually running and visible to users. The catalogs, databases, and tables, including table schemas and table properties, should all be in code, because if it's not in code, you're not able to deploy a debug version of it to test against. And then, of course, you have to make sure that your production actually matches your code. You have to modularize and unit test your code. Down here I've got it. I don't use any notebooks in production. All of my work I'm doing in a code editor. I use PyCharm, my colleagues use VS Code, and we build a Python wheel, and then the Python wheel is pushed into the Databricks workspace, and all of our jobs are running directly against the Python wheel. It also means you resist the temptation of changing something in production live, because the only way to change it is to make the change in the code and then ask your deployment job to actually push a new Python wheel. You have to make your code testable, and that's the part that I showed you some details of how I do this. My tooling library, I would say, is not the important message here. The important message is you have to have some tooling. You have to have something to do this with. There's a quote from NASA, which they did sometime in the 90s, test as you fly and fly as you test, which means make sure your tests are actually representative of the way that it's going to be used, because you can test a ton of stuff. For example, when I said this about the tables and testing against the actual table structure that you are running in production, we used to. This is all like everything here is coming from bitter experience. We used to have a lot of tests where someone wrote, well, this is the code, this is the table, how it should look in production. And then they wrote a unit test. And then their unit test, they made a nice description of what an incoming data frame would look like and then what an outgoing data frame would look like. Problem was, and then the tests were good. Problem was that the incoming data frame looked nothing like the table that's actually in production. So that's why test as you fly for me means make sure you're testing what you think you're testing. Don't just test some fantasy, which is not representative of what the environment will look like that you meet in the real world. I recommend the PR flow, where you do code review, and then make sure you deploy your table changes so that the tables in production actually look the way they're tested. That's it. If you want my code for the tooling library, that's open source. You can use it. It's not just me. It's a group of my colleagues who are also contributing to that, and I know of at least 5 production systems which are currently using that and contributing to that tooling library. So that was a big success. And do get in touch on LinkedIn. Are there any questions? Go ahead.
Just because it's at top of my mind, you said that you have the catalog schemas and everything as code.
Yeah.
What do you use Terraform for setting up the catalogs?
I use Terraform for the catalogs, but the databases and tables are in my Python library, and the Python library also contains the tooling to change that. Because the Terraform provider actually has a way to deploy tables, and it actually, in the documentation, it says to not use it. Because if you use the Terraform provider, you don't have direct control over how it will apply those changes to the table. And anyway, you need a cluster to be able to change a table. And I think the Terraform provider also says it will spin up a serverless SQL cluster to apply the table changes. But I don't use that.
Because I found out that the asset bundles, they don't support catalogs just recently.
Really?
You can deploy the schemas there, but not the catalogs.
Okay. Yeah, I do use asset bundles to deploy my jobs. I basically every combination of how you can do it, I've used in some context. For the main stuff that I use, I deploy the infrastructure and the catalog from Terraform, and I deploy my Python wheel and the jobs in a bundle, an asset bundle.
Okay. So the clusters are Terraform, straight Terraform.
Clusters are part of my job description, and that's an asset bundle.
Okay.
And I don't use general purpose clusters for production. It's all job clusters. All right. Well, then that's it, I guess. Thank you for listening. All right.
It's interesting to get your view on this because I think we've been in the data space, we've been lacking. Basically, we have been writing code.
Yeah.
But it's a little bit different, and the context is a little bit different. But we have been slow to pick up on changes that happened in software development. I'm going to say tens of years ago.
Yeah. Yeah, definitely. That's also like part of the core message here is that we are not special. There are people who have done a lot of similar stuff for a very long time, and they have written entire books and university courses on how to do testing in software systems. And in the end, a Databricks data platform is a software system. And every software system, because people think, oh yeah, but we have a lot of data. But every software system has a database, basically. If it does anything useful, it's probably going to have a database in it. And those databases need to be evolved, and they probably have valuable long-term data also. So we're not that special. It's just that a lot of people, I feel a lot of my colleagues coming into this are not formally trained software developers. They are usually trained in some way to do data, business analysts, scientists like me. I was able to learn, so they should be able to learn to do the proper engineering techniques of having good control of what system you're running, and not just let it flow freely and evolve freely. There are also pieces which are not even in my slideshow, such as how do you do monitoring? How do you monitor your data quality? How do you get the alerts? Because if something breaks, a person needs to know to be able to fix it. So we use Slack, and we have integration all the way down in our code, where of course if the job fails, we get a Slack message. But sometimes you don't want the job to fail. Sometimes you just need to tell someone about something that's a bit off, and we also have Slack integrations for that, and stuff like that. Yeah. So there are more pieces, and there's a tons of stuff in the. If you go to this website, we also have a complete template project where we set up an entire data platform with Terraform, with unit testing, that you can just take a copy of and deploy. And I've actually heard of one person who doesn't know me and who's tried it, and I think had some success. So it's possible.
Yeah, I think he was going to be here today, but obviously not.
All right.
Yeah, I think it's an interesting topic. I mean, as Pablo points out in yourself, I mean, the data space has been lacking from the software development space in terms of CI/CD and just software development best practices. But
Yes.
it's also the vendors, the tooling available to us.
Yes.
Have been promoting that.
Yeah.
So looking at like vendors like Databricks and the likes, I mean, if you're doing software development on a traditional like SQL-based database, you might have something like Flyway or something to kind of evolve your schema over time and version control your DDL. You have none of that in Databricks.
That's right.
So it's not just the people, it's also the kind of tooling and vendors.
And yet, I feel that Databricks is much better here than the competition. We've had people who tried. Personally, I was lucky to not have to do that, but people have tried the Synapse, and it was just hopeless in terms of some things were just not at all possible to do in any other way than just clicking your way through it. But Databricks at least has an API-first approach to absolutely everything. Everything you can do in the interface, you can also do in an API. So that's really helpful.
But on the contrary, they come from a notebook, very notebook-heavy kind of ecosystem, which is inherently difficult to.
They come from a notebook-heavy ecosystem, but it is possible to do everything without touching notebooks, which I recommend because it's easier to use software development tools if you use if you write real software than if you do notebooks.
So if you write modular software, then you can.
Yeah.
Sure.
Yeah. I mean, when I say I don't use notebooks, I mean I don't use it to run any of my production transformations. I do use notebooks, of course, to do exploration and to test, just to look at tables and what happens if I do this join and stuff like that. Of course, I do that. But then it gets put into a Python library before it gets deployed to production. Yeah. All right. Then I'll
I'm
guess.
curious about your, seeding of data for the tests.
Yeah.
Do you use real data, real tables, or?
So real data has the problem of being very large and then your tests take a long time because they have to transform a lot of data. So most of the time, the first 60% of problems can be discovered just by running against empty tables, I would say, because oftentimes this, I don't know, you thought this was a Boolean, but it's actually a string containing the words true or false, or stuff like that, and just make sure that all of your schema works all the way through. That's the first step, so that it doesn't break when you actually try to run it. Then having data is oftentimes something which is. Oftentimes people ask us to add features, and then the source data isn't ready yet. So we start running pipelines which are doing almost nothing, and then after a while some data gets through, and they look at the result, the kind of gold layer or the Power BI reports, and then they find out, oh, it's not actually looking the way we want it. We have to go back and update it. Sorry. And so that's exactly what this piece of the puzzle is. This V model. That's exactly what this is about. They ask you to do something, and then they ask some other system to do something else, and you do your stuff perfectly because you've written a unit test. But then they find out that at the top level, that wasn't actually the thing they should have asked you to do. and then you go around and you iterate and you change it, and they change your requirements, and you change your system, and then you integrate again. And so that's why you have to test at every level. So it doesn't make sense to test everything. It only makes sense to test up to a point where you think you've fulfilled what you need. You made sure you don't break anything else that already works, and you've so oftentimes I will, maybe if I have to ingest some raw data from an event hub which has some JSON schema, I will maybe choose a day which I know has data, or an hour, and I'll try and ingest that in my unit test or my integration test to check, can I actually read JSON data? Does anything get through, or do I just get all nulls? But so in some cases you do that, but then if you use real data from a real system, then you're not in control of what that data actually shows, and so it's very hard to make assertions on that. So I usually use integration tests where I check, can I read something, and does everything run through all the way? And then I use different tests, which I call unit tests, where I write a data frame, and that data frame contains all the behavior that I have written my ETL code to be able to, filter or explode some array and stuff, and it will contain like examples of that, and then I'll show what does that look like behind.
But then at some point you're going to hit reality, right? And you're going to be exposed to
Of course, but that's what happens when you join, because our data platform is not a product in itself. It's a piece of a corporate ecosystem of where the company offers some products to customers, and our data platform is fulfilling one function of the product, of the experience that the customer is seeing, and so you cannot do everything by yourself, or you could, but it doesn't matter how well you do it, because in the end, when you get to integration, someone might have made a mistake with what they asked you to do, even though you did it perfectly. What they asked you to do was wrong.
Of course, I was just wondering, about the practicality of it, doing I guess the acceptance test then on your staging environment or wherever, right? And
We of course also we do a lot of testing actually in production also, so these debug tables, they don't interfere with our real tables, so we actually create them also in our production system, because then, for example, in the production system you will have, because you, of course, as you should, your staging database has a different password than your production database, right? And so does your code run against the staging database, some external database? Does it have the right keys to be able to access that? Did you set up all your permissions in your Terraform? And then you can ask the same question, does it also work in production? Because sometimes you set something up and someone somewhere set a policy that all passwords should end after 2 years, and then your production system was deployed later, and then so at some point your staging system fails, and you're like, damn, luckily my production system only, like, the password runs out a bit later, and then you have to hurry up, fix that. But sometimes people have, deployed to staging and everything works, but the other team forgot to press deploy to production. And so you have to, some pieces you do actually have to test in your production system. Yeah. Yeah. Anything else?
Great.
Right.
Thank you.
Well, thank you for listening.